Okay, so scissors congruence of polyhedra is what I can you hear me? So scissors congruence of polyhedra is what I want to introduce you to. And to do that, I want to start with some very familiar formulas that just about everybody learns in fairly early in your education for things like areas and volumes. So the most basic is the area of a rectangle is base times height. And then we have the area of a parallelogram, which is also base times height. And we have the area of a triangle, which is 1/2 base times height. Now, some people are aware of where these kinds of formulas come from, but most people aren't. Most people are taught these formulas before they are mature enough to be ready for explanations. So they are just sort of received wisdom. So we could ask the question, where do these formulas come from? I mean, who discovered them? What were they thinking? And the answer is that these formulas, and many others like them, were known to the ancients. The ancient Greeks in particular, and many other cultures had explored geometry. But that raises the question, how did they figure them out? Maybe they were asking, you know, who before us figured these out? Let's start with the easiest case, which is the case of a rectangle whose base and height are both whole numbers. So in this case, we can dissect the rectangle into unit squares. And the number of unit squares is going to be the base times the height. So in this case, 4 times 3. So we'll have 12 unit squares. So that explains, in a sense, why we would expect the area of a rectangle to be at least proportional to base times height. And this, of course, would work for any rectangle with whole numbers for base and height. What happens if the height is fractional? Well, the same argument doesn't quite work, because if you try chopping up the rectangle into unit squares, you're going to get little scraps on the end. So you're going to have some wasted area there. Now you can try to collect the scraps together and assemble more unit squares out of it, but at some point it's going to get to be kind of a confused process. And you don't expect to get a whole number of unit squares, of course, if the area isn't a whole number. So how do we make sense of it from a dissection point of view in this case? Well, there is a very clever idea, which I think very few people have actually seen. This is a very charming little construction. Suppose you have two rectangles, and they both have this, they should have the same area in the sense that base times height is the same for both. So what we'd really ideally like to know is if base times height is the same for two rectangles, then we can justify the fact that they have the same area. And if base times height is not the same, then they should not have the same area. Or another way of saying that is, if two rectangles have the same area, then base times height is the same. So I've illustrated this with two rectangles. One of them's a little bit taller and a little narrower, and the other one's not as tall, but it's wider. But I'm assuming that base times height is the same for both. You start the construction by laying down a foundation of B prime under the rectangle whose base is B. So we're preparing the ground, like we're going to do some construction, and we have a new foundation that's B prime wide. And now we take a pair of scissors and we snip through the rectangle. We're going to cut along the upper dotted line, but the lower dotted line is also helpful as a sort of tracking or guide rails. And now we snip off that corner triangle and we slide it down. Now we cut across and we snip off that little triangle in the upper left and we slide that down. And lo and behold, this triangle has become like the one on the right. So we say in this situation that the two figures are scissors congruent. So scissors congruent in general means that you can dissect one of the figures into pieces, and then you can translate the pieces to reassemble the other figure. Now there's many variants on this concept. In some variants you're not allowed to rotate the figures as you translate them. In some variants you're allowed to rotate them. And there's even more far-flung variants. Generally speaking, in the plane, we're not going to need to do much rotation. We need to do a little bit of rotation, but not much. I'll show you an example where we need to rotate. Parallelogram can be handled similarly. The parallelogram can be snipped along two dotted lines, and we'll slide the middle section over, and then we'll slide the little triangle over, and it has become a rectangle. And that justifies the fact that a parallelogram is scissors congruent to a rectangle with the same base and the same height. And therefore, its area must be the same as the rectangle. And so that's where we get the area formula for parallelogram. And then for a triangle, we can do essentially the same thing with a triangle, but let's mix it up a little bit. I'm going to prove the formula area is 1/2 base times height by duplicating the triangle. So there's now two triangles there. I've made a copy of it. And I'm going to rotate the triangle around 180 degrees. And when you do that, it becomes a parallelogram. And so we've reduced to a case we already understand. So the area of this figure, this parallelogram, we now know is base times height. But it's twice the area of the triangle. So we get twice the area of the triangle is the area of the parallelogram, so it's base times, so the area of the triangle must be 1/2 base times height. So those kinds of arguments were very familiar to the ancient geometers. They also, the ancient Greeks had a method of exhaustion that was a sort of a precursor to the calculus notion of infinitesimal subdivisions, but I'm not going to address that. And those wouldn't be considered scissor congruences, but they're related. They're a related concept. They also thought about algebra in the same terms. And a vestige of that is the fact that we talk about squares and cubes in algebra. Why is x times x a square and why is x times x times x a cube? Of course, those are the formulas for the area of a square and a cube and the volume of a cube. And they still linger, even though almost nobody ever thinks of algebra in geometric terms anymore. I do, but I'm fairly lonely in that. I've illustrated one of the most basic principles in algebra, FOIL. If you multiply two binomial expressions together, you get 4 terms. The first term is usually designated F because it's from the first of each of the pairs. And then you have O, I, and L. F is A times C, and it's the area of the lower left subdivision of this rectangle. O is A times D, the outer terms. That's the upper left. Oops. Spoiler. I is B times C, and that's in the lower right. And L is B times D, it's in the upper right. So FOIL is, if you add the four terms of FOIL, you are adding up the areas of the pieces of a dissection of the rectangle. The area of the rectangle itself is A plus B times C plus D, because the base is A plus B, and the height is C plus D. And the venerable Pythagorean theorem can also be understood in these terms. You know, there's hundreds of proofs known of the Pythagorean theorem. There have been presidents of the United States in more enlightened eras that, that have discovered new proofs of the Pythagorean theorem. Try to find somebody who even knows one proof these days. Anyway, you'll know one proof in a minute. So the Pythagorean theorem says that if you have a right triangle with legs A and B and hypotenuse C, then C squared equals A squared plus B squared. If we are reminded that squares are, algebraic squares are areas of geometric squares, then we could maybe anticipate that perhaps a square of side C could be dissected and reassembled into a square of side A and a square of side B. And that would be pretty cool if that were possible. In fact, in some sense, we know it has to be possible, because any two figures with the same area in the plane are scissors congruent. So let's see how it's done. There's many ways to do it. The way I'm going to show you, I think, is particularly appealing. So we erect a square on the hypotenuse. And the hypotenuse has length C, so this is a square of area C squared. And for convenience, to comprehend what's going on, I'm going to surround this square with a bigger square whose side lengths are A plus B. Notice that as we go around the perimeter of the big square, the circumscribed square, the letters go A, B, A, B, A, B, A, B. That means that on opposite sides of the square, A is opposing B, and B is opposing A. Now we do a really clever subdivision of that inner square. You have to stare at this for a while, but this is something that people sometimes call a proof without words. You have to stare at it for a while until you realize that the little triangles inside that square have to be congruent to the original triangle. For instance, say the red triangle on the side, its height is A, and its width is B. And that is, you can see that from elementary geometry, because if you rotate this triangle, the original triangle in the lower left corner, it will become the triangle in the lower right corner, and so on. You can rotate it around in all four positions, and it will trace out the square in the middle. So now we have four triangles congruent to the original triangle, and we're going to slide them around. So I'm going to slide the yellow triangle first into the position where the original triangle was. And now I'm going to slide the red triangle, and I have a new figure. and I'm going to dissect it differently. So I'll erase all those inner division marks and simply divide it like that. And now we see that this is a square of side A with a square of side B resting on top of it. So the area of this is manifestly A squared plus B squared. The original figure that was created from had area C squared. So there is a proof of the Pythagorean theorem. So we can now pause and ask the question, what do we have to learn from these things? If this was done in ancient times, does this have any relevance to modern mathematics or modern science or the modern world at all? Well, I think it's generally speaking unwise to dismiss the insights of ancient civilizations. There is a very good reason that they were fascinated by these kinds of things, and these kinds of geometric investigations have been a constant in all of known human history. So right up until the present day, dissections of polyhedra continue to be studied and to turn up all kinds of new fruitful connections, sometimes very surprising and very far-flung from where you might expect to see them. There's indications that they're going to show up in modern physics, the most abstract modern physics, which we might think would be as far from this kind of stuff as conceivable. I'm going to raise what I call a big question. This is more of a philosophical question, but I think that this is well worth pondering. What does it actually mean for two things to be equal? So I started with this equation: the area of a rectangle is base times height. There's a whole lot of presuppositions. If somebody asks you to prove that, you have to ask a lot of questions about what do you mean by prove it? What do we think we know about area that we have a basis to prove anything? And what do we mean by saying that one thing equals another? In what sense do two scissors congruent figures have the same area? I contend that the kind of thinking that we use, and which is put in really sharp relief in this context, is the kind of thinking we use in almost any part of mathematics and really in almost any human endeavor. So we're analyzing something, we're comparing the parts, and we're using some kind of a process to bring the parts of corresponding objects together so that we can directly compare them. You always have to have these elements, I believe. You have to have a notion of dissecting something, analyzing something. And the root etymology of analyzing is suggests cutting something up. So you have to have an agreed upon notion of how you're going to consider it legitimate to cut up objects, and then how are you going to bring the pieces of those objects together so you can compare them? And then what do you mean by comparing them? So I think this is a paradigm for a very fruitful kind of general investigation. So at its most basic level, in my opinion, we could roughly summarize mathematics as involving measurement, comparison, equality/comparison, and shape. And that those correspond, I think, roughly to the strengths that we as a species have. We have a particularly well-developed visual cortex, and we, of course, have a highly developed language faculty. And I think that's why this serves for me as a sort of a model for all investigative processes. Another thing to note about this is that equality is a process. Equality is not something static. You don't just glance at two things and decide instantly whether they're equal. It's certainly not obvious that the Pythagorean theorem is true. We don't just glance at a right triangle and suddenly pops into our head that c squared equals a squared plus b squared. There's some kind of process involved in bringing those pieces together. You have to do something to show two things are equal. This is a perspective that's actually has the spotlight on it these days. I think this is going to become more and more a focus of current research in math, where we no longer think of identity as the most fundamental way that we relate things in mathematics. We use the equal sign a lot, but what does it mean that two things are equal? In algebra, it's very commonplace to see long calculations. You might do a paragraph or a page of calculations, and you have things on two sides of an equation, and finally at the bottom you can say that they're the same. It's a little bit like a scissors congruence. You're manipulating the little parts, you have to break things open, you have to distribute expressions, and then you have to finally match up the pieces and see that they correspond in some sense. I want to point out another example that's analogous to this and is actually a special case. Hume's principle, Hume is by many considered as kind of rock star in the world of philosophy. He doesn't look like a rock star, but that's how they looked in those days. So he, in his treatise on human nature, he writes, "Algebra and arithmetic are the only sciences in which we can carry on a chain of reasoning and preserve a perfect exactness and certainty." Okay, he's doing well so far. "When two numbers are so combined as that the one has always a unit answering to every unit of the other, we pronounce them equal." This is sometimes called Hume's principle. And what he's saying here is what we would in current terminology call a one-to-one correspondence. He's saying if you can match up each element of one set with one element of the other set, then there must be the same number of elements. So for instance, if you're at a dance and there's a whole, well, I have a graphic. David Hume goes on to, I think he kind of lost it though at the end of the sentence. You notice we end here on a semicolon, and then he goes on and says, "And it is for want of such a standard of equality in spatial extension that geometry can scarce be esteemed a perfect and infallible science." Well, I have to get my red pen out at some point and put some marks here. So are there more green or more red dots? This is the big auditorium, and it's a dance, and the greenies like to dance with the red dots, and it's always nice when nobody gets left out. So if we leave it like this, it's not obvious, but I'm going to let them migrate towards each other, and now we see they indeed are equal in number. So it's a process of bringing together and forming a one-to-one correspondence. And we could also indicate the one-to-one correspondence with the original positioning if we just drew line segments, or we can draw any kind of figure we like to connect them. It's worth noting that counting is really forming a one-to-one correspondence between a known set, say the numbers from 1 to 20, and a set you're counting. You're actually, as you're counting things off, you're actually making a one-to-one correspondence with this known set. And this is typical of how we measure things. When I was talking about the area of a rectangle, I said, for instance, the original rectangle had 12 unit squares in it. I'm not particularly concerned what we count the area of a unit rectangle as. I mean, it's usually taken to be 1, but it really doesn't matter. I'm happy to just say that a rectangle has, that rectangle has 12 times the area of a unit rectangle. But in general, for practical reasons, we sometimes have standards and measures. So we have rulers. We decide, the international standards bodies decide on what the unit of a kilogram is and a meter and things like that. And so we can compare things in general abstractly, but sometimes for practical reasons we compare to specifics. I want to point out also that this kind of thinking is behind at least 2 revolutions that are relatively recent historically. One is Cantor's theory of infinite cardinalities. Cantor based a theory of counting infinitely large sets on this idea of one-to-one correspondences. And he was his analysis was deeper than anybody had taken it before, and he was able to resolve some of the confusions people had about this question, and it led to a tremendous revolution in the foundations of math. One of the things that blew people's minds in the late 1800s was that Cantor established that there's different sizes of infinity. Before that point, people thought of finite sets as having sizes, and then beyond that there's the, I have to get used to this, beyond that there's the infinite, which is unmeasurable. But we now know, because of Cantor's work, that the infinite is actually measurable. So this is an example of taking very seriously this idea that we have to be very careful about what we mean by analyzing an object, by what kind of dissections we consider valid, and how we compare two things. And when we do that very carefully without relying on our gut reactions or our instincts or what our ancestors might have wrongly informed us, we can sometimes find revolutionary and beautiful new areas of research. Another example is Einstein's theory of relativity. Einstein's original paper on special relativity is exactly in the same paradigm, where he's very carefully looking at what it would mean for two observers in different inertial frames to be measuring the same quantities. And you can ask things like, can we establish simultaneity? Are we going to measure the same lengths, the same durations? And in that situation, we don't translate triangles across a plane. We use light rays to communicate from one place to another. And again, it was Einstein who got to a deeper level of understanding on what was really foundational, what we really meant by measuring things like this. And then, of course, there were new assumptions about how light moves, which had to figure in. Here are some polytopes. These are beautiful objects that have been studied since ancient times. These are close to my heart. I've done research on polytopes since I was a graduate student. And these are also the object of scissors congruence studies. I did my PhD thesis on this, and I did work on something called the polytope algebra, which is a framework for studying the scissors congruence of polyhedra in arbitrary dimensions. But this is a fractal. This is a Sierpinski triangle. And this is an exotic object from the point of view of ancient geometry. The Greeks did not know about this. Things like this were not studied until the past 2 centuries. And only fairly recently have they been given a great deal of attention. But they're manifestly gorgeous. They are fascinating. The characteristic of a fractal is that it repeats, it has self-similarity. So you see the same shape repeated inside the shape. It's a kind of recursive structure. We see this kind of recursive structure in many areas that we focus on in research. And they're just, I think it's almost self-explanatory that they need to be studied because they're just so beautiful. To my knowledge, there is not yet a theory of scissors congruence of these kinds of figures. And I think it's a hugely interesting area to look at because I believe that the notions of dissection that we use in classical geometry are probably going to be inadequate for this. And I think we'll probably have to have a newly adapted notion of dissection. What do we mean? I think we need a fractal dissection of a fractal figure. These are all artificially generated figures. 3 of them look pretty artificial. The 4th one kind of looks like a plant, though. And we actually see fractals everywhere in nature. Benoit Mandelbrot was the one who really brought this to the attention of the world. He wrote a book called The Fractal Geometry of Nature in 1982, I believe. And he had been studying fractals in nature for a few decades before that. And he spent a lot of his life sort of evangelizing the idea that we don't see circles and squares and triangles in nature. We see fractals. I mean, not that circles and squares and triangles aren't worth studying, but he made this point very emphatically that we're treating these things as if, you know, the shapes of plants and mountains and coastlines, as if there's some kind of imperfect version of a circle. They're actually an interesting new kind of geometry. This is a Menger sponge. And this is part of the Mandelbrot set, named after Benoit Mandelbrot. This, I believe, is zoomed in probably several tens of thousands of times. So this is just a little detail of the Mandelbrot set, but it's, would you believe if somebody told you that this came out of a simple equation in math and that wasn't produced by an artist selling posters at a Grateful Dead concert or something? This is a Romanesco broccoli. I brought one of these into one of my classes once. I was surprised that my students had never seen one. I even had a vegan student who wasn't aware. These are absolutely beautiful plants, and they're, I like them better than the regular kind of broccoli, so I get these fairly often. But they have an amazing fractal structure. They're like works of art. And stock prices are believed to be fractals. Mandelbrot himself, that was one of the things he studied. And climate data looks pretty fractal. This is an abstract of a paper by Mandelbrot. How long is the coast of Britain? And I'm just going to read the first few sentences. Geographical curves are so involved in their detail that their lengths are often infinite or rather undefinable. However, many statistically self-similar, meaning that each portion can be considered a reduced scale image of the whole, like the Sierpinski triangle. In that case, the degree of complication can be described by a quantity d that has many properties of a dimension, though it is fractional. So Mandelbrot is emphasizing this view that we've been studying things of dimension 0, 1, 2, whole number dimensions for a long time in geometry, but the fractals are really objects that have fractional dimensions, so in between 1 and 2, say. And for that reason, you can't really measure the length of the coast of Britain if you're using an ordinary ruler and you're measuring it as if it were a smooth curve. It does, in some sense, have a length. We might not call it a length. but it needs new kinds of tools to quantify it, because the smaller the scale you go to, the longer it's going to seem. And that is the essential property of fractals that fascinates me, and which I think makes it quite, it fits in with the kinds of mathematics people have used in the past to study scissors congruence. And I finish with Shakespeare's Sonnet 18. This doesn't seem to have anything to do with anything, does it? Shall I compare thee to a summer's day? Thou art more lovely and more temperate. Rough winds do shake the darling buds of May, and summer's leaf hath all too short a date. I just want to point out that poetic metaphor seems about as far from geometry as you can get. But on some level, it's really a similar kind of thinking. So with a metaphor, you dissect something that you are trying to describe, and you compare its parts to something else. And I find this particularly interesting because Shakespeare is sort of doing a comparison on two levels. He's on a meta level at the same time as he's talking about this comparison. His object, his devotion here is somebody he's comparing to a summer day, but he's putting a question mark beside it. Should I compare you? Because, summer isn't as great as it's cracked up to be, maybe. And so he's, at the same time, he's sort of playing with the tradition, where this is a very common kind of theme in poetry, and he's comparing his own use of this device to other poets or his own prior poems. So I think there's a reason that the verb to be is the second most common word in the English language. This is the kind of thinking we're always doing, and I think that domains like scissors congruence really put in sharp relief exactly what we're doing when we're comparing objects, dissecting them, and bringing them together. Do you know, the reason I wanted to present scissors congruence here is that I think that it has a really direct appeal. It's hard to get a rise out of people when you talk about math. But if anything does, it's something like scissors congruence and fractals, things that just directly stimulate our visual aesthetic sense. So I would not be surprised at all if school children would find it amusing to play games with scissors congruence. There are actually games where you dissect pieces and reassemble. You can take apart a rectangle and make a little dinosaur out of it. The children seem to enjoy those. I don't know why they wouldn't enjoy seeing derivations of formulas like this. Well, in an ideal world, I'd present as many proofs as I can get away with. I remember an author once who wrote a science exposition claimed that his publisher warned him for every equation that you put in your book is going to reduce your readership by 10%. So people people fear math. I mean, we've discussed this a lot. You know, in the world of pedagogy, these kinds of questions come up a lot, and it's sometimes compared to something like the field of music, where nobody becomes a music major without an independent interest in music and a lot of exposure to music and having listened to lots of beautiful music and probably tried to write music and play it. But it's a radically different experience studying math in school, where the students are taught as if they have no independent interest in math at all, and we just kind of have to ram them through the program. I mean, of course, that's not how I like to think about the process, but that's the nightmare scenario we want to avoid. But it's you know, if there were an easy way of, you know, magically making the entire curriculum some, you know, wonderful, exciting, charming experience, I think we'd already be doing it. Yes?
What's your name and the title of the presentation?
My name is Robert Morelli, and the title is Scissors Congruence. So, yeah, anybody who's interested in following up or learning more about this, my office is in the SI building. I'm available. Yes?
So, just kind of going along with this final portion of fractals and the poetic metaphor, if we look at writing being a word, then to a sentence, then to a paragraph, then to a section, and then just kind of the way that it has that fractal relation, would it be not safe, but I guess would it be safe to make the comparison like that math, or that art is an extension of math and vice versa, math is an extension of art, they're both coming as a creation type inquiry?
Well, first of all, mathematicians and many other allied sciences use a lot of aesthetic language. So we talk about a proof being elegant, we talk about results being beautiful, and we're especially guided by aesthetic instincts when we're doing research. And many mathematicians, research mathematicians, doubt that you actually could be successful in research if you weren't guided by aesthetic principles. So this is, it's something of a mystery, actually, why mathematics is beautiful to us. It doesn't seem to have obvious fitness value. It doesn't seem to be something that a prey animal could use to escape being eaten. But it is absolutely universal, and almost every successful mathematician speaks quite freely about, you know, mathematics being essentially an artistic endeavor. And mathematicians are generally driven by that artistic sense, the aesthetic sense. They're not driven, most of them are not driven by specific applications. Whether art is an extension of math, well, my personal view is that human beings are the mathematical species on the planet. I think everything we do is mathematics. And I think the universe is made of mathematics. I think there really isn't anything meaningful outside of mathematics per se. It's just a question of how pure and how deeply you're studying it and what tools you're using. But yes, I think art is, I mean, we can, you know, how many ways can you chop up 4 beats to make different rhythms? I mean, we just take pleasure in hearing dissections of rhythmic structures in music, and it's analogous, and we see these kinds of processes everywhere in art. And it has the same hierarchical structure like we were talking about with writing.